Okay, so these are basic probability scenarios, and they're kind of a good taste of what you can expect from the basic probability section of this unit. So 5 multiple choice questions, each with 4 possible answers, appear on your history test. So we have 5 questions, and each one has 4 possible choices. And let's just say the choices are A, B, C, and D, one of which will be correct. So 1 is correct and 3 are wrong. I just said A was correct, but I could have chosen anything. So the probability of guessing correctly is 1 out of 4. The probability of guessing wrong is 3 out of 4. So the first question is, what's the probability you get none of the questions correct? Well, how many questions were there? Well, in this particular case, we know we had 5 questions. So that means I need 5 blanks, 1, 2, 3, 4, 5. And I got none correct. That means every single one of them were wrong. So I fill in the blanks and I go 3/4 times 3/4. And by the time I get to this, I'm tired of writing 3/4, and that is fine. You can sit there and go, you know what? I know I could write this as an exponent, and that would be absolutely correct. You could put 3/4 to the 5th power, because that's the probability of getting wrong in the first, wrong in the second, wrong in the third, wrong in the fourth, and wrong in the 5th. So my work shown would be simply 3/4 to the 5th power, and you could write the answer as a decimal or leave it as a fraction if you chose. The next one is, what's the probability of getting them all correct? Well, once again, I have 5 questions and I need correct on all of them. What's the probability of getting correct? Well, probability of the first one is 1/4, but since I'm just guessing, they're all independent, and so it's 1/4 times 1/4 times 1/4, which is basically 1/4 to the 5th power. And once again, I like starting off by writing the blanks and filling in, and then as soon as I recognize what I'm doing, I'll write it as an exponent and solve it, okay? This one, part D, is one of the most difficult questions of all, and students struggle with it. If I see the word at least one, and I'm specifically looking for at least 1, I'm not looking for at least 2, I'm not looking for at least 3, we'll do without in a later unit, but at least 1 is the most difficult. So at least 1, I'm going to go 1 minus, and let's talk about that. I have 5 questions. So basically I could get 0 wrong, 1 wrong, 2 wrong, 3 wrong, 4 wrong, or 5 wrong. I want at least 1, which means 1, 2, 3, 4, 5. That's what I'm interested in. What I'm not interested in is the probability of 0. Well, what's 0 wrong? 0 wrong is the probability of all correct. So I could just go 1 minus 1/4 to the 5th power. And that way I can do that fairly easily. And that's 1 minus the probability of getting them all correct, because I wasn't interested in them all correct. So if I say, hey, so anytime they say at least, do 1 minus whatever they were asking for. They were asking for wrong, so we worked with correct. All right, that should be 1/4. Okay, all right. Get your first incorrect answer on the 4th question. And I'm just telling you, the blank method works so well for this. First incorrect on the 4th question. That means this is correct, this is correct, this is correct, and this is wrong. The probability of wrong is 3/4, and the probability of correct is 1/4. Now, in this case, I probably would have filled in all the blanks, but it's not wrong to have written 1/4 to the 3rd power times 3/4. Okay, the Master Foods Company manufactures bags of peanut butter M&Ms. They report that they make 10% brown and red candies, 20% yellow, blue, and orange. The rest are green. All right. If you pick a peanut butter M&M at random, what's the probability that it is green? Well, here's the deal. They didn't tell us that. But what they did tell us is 10% chance of brown, 10% chance of red, 20% of yellow, 20% blue, and 20% chance of orange. And we know to be a valid probability distribution, it all has to sum up to 1. So if I just take 1 minus those probabilities, the probability of brown, red, blue, orange, and green, first off, this adds up to 80%. So 1 minus 0.8 tells me the green has to be 20%, so that it adds up to 1 whole. Then it says, what's the is a primary color red, yellow, or blue? Oh, this is an or. Or indicates add. So I'm looking at the probability of red, yellow, or blue, and I'm plugging into the 3 blanks. So there's a 50% chance that it's one of the other. What's the probability it's not orange? Well, the probability of orange is 0.2, so not orange would be 1 minus 0.2. This is also known as a complement, all right? A complement is the not scenario, and we'll talk more about that in the next video. If you pick 4 M&Ms in a row, what's the probability that they are all blue? So we have 1, 2, 3, 4 blanks. The probability of blue is 0.2. Oh, so basically it's 0.2 times 0.2 times 0.2. And by the time I get to that second one, I figured out that I just need to go 0.2 to the 4th power, and that's fine. What's the probability none are green? Gosh. Well, what's the probability of green? 0.2. So not green means first off, we're doing 1, 2, 3, 4 blanks. And we want not green, and not green, and not green, and not green. So green is 0.2. So probability of G equals 0.2. So not green is 0.8, or 1 minus that. And again, you could have done 0.8 to the 4th power. At least one is red. So once again, here's that horrible thing that says at least. As soon as they say at least, you need to be thinking 1 minus. All right. So once again, we could have all these colors: brown, red, yellow, blue, orange, or green. We know we have 4 blanks: 1, 2, 3, 4, because we're doing this 4 times. It says at least, so that's 1 minus. And we want the probability that it's not red. Our probability of at least one is red. Since they asked for red, we're going to do the opposite of what they asked for. So this is going to be 0.9 times 0.9 times 0.9 times 0.9, because the probability of red was 0.1. Probability of the R equals 0.1, and we're going to do the opposite. Please remember, we did the opposite up here as well. At least one question wrong. So instead of doing wrong, we did right. Okay, so whatever they do, whatever they ask for, when it's an at least one, you're going to do 1 minus the opposite of what they asked for. So they asked for red, so the opposite of red would be not red. All right. And finally, what's the probability? The 4th one is brown. Well, that means we have, I'll do this on a separate sheet of paper. We have 1, 2, 3, 4 blanks. This is brown, not brown, not brown, and not brown. The probability of brown is 0.1. The probability of not brown is the 0.9. And since I have to have not brown and not brown and not brown and then brown, I have to multiply those. All right, number C is a tricky question, and I'm going to go ahead and put this up on the screen. After picking 10 M&Ms in a row, you still have not picked a red one. A friend says that you should have a better chance of getting a red candy on your next pick since you haven't seen one. Comment on your friend's statement. And your friend is right if you're drawing out a single bag of M&Ms, because in which case It's a dependent, they're not independent. And every time you draw an M&M, the number of M&Ms changes. And so consequently, your probability increases. However, if your friend's talking about the immense, massive quantity of M&Ms that are ever produced, your friend would be incorrect. And although he's technically correct, we like to say that they're incorrect in that the probabilities are essentially the same. Consider this. Consider the millions and billions of M&Ms that were selected, created this year. If I eat one of them, the percentages change. By how much? And the answer is not much. And since they didn't change by that much, we say they're still independent because it has little or no effect on the next pick. And you're like, well, how big is big? Honestly, we'll talk about that in the third quarter. But for right now, consider this. If you're drawing from a single bag of M&Ms, the percentages change and they're dependent events. But if you have a massive, massive quantity, you can sit there and go, negligible, no effect. All right. And we'll talk more about that next quarter. But for right now, we're going to be focusing on the fact that they're dependent. However, please remember what's happened in the past does not impact the future if it's an independent situation. So if we're rolling a dice and it's like, I've rolled it 100 times and I still haven't gotten a 6, the next roll is still a 1 in 6 chance. The past will not impact the future for independent events. All right, thank you.